So this lecture, unlike the previous one, is going to be discussing a little bit more practical things. Well, practical is a strong term for what we're doing, which is just pure math. But we're going to be discussing real tools. So this, if you are familiar with the literature in zero knowledge, you'll see that these things that we're going to be discussing today, so things like the zero check or some notion of sparsity check, have probably popped up in your study of ZK protocols. So the aim of this lecture, for the most part, will be to rewrite a lot of those tools, not just from the perspective of I guess taking a quick step back, most of those tools, as I mentioned before and alluded to in the previous lecture, are usually kind of dependent on things like, okay, we want to check that a polynomial is zero. And instead of checking the whole polynomial is zero, it suffices to check that the polynomial evaluated at a random point is equal to zero. And then that means with high probability, the whole polynomial must have been zero in the first place. So that statement has an equivalent analog for in error correcting codes, right? And we're going to discuss that here. And not only are we going to discuss it here, we're also going to give kind of what that analog is and a proof of that analog in very simple notation. And by virtue of the fact that, we've kind of eaten these vegetables, we've kind of done the linear algebra part, we've done these weird probabilistic implication stuff, we're going to get just kind of as a side effect of that, we're going to be able to write proofs that traditionally take kind of quite a bit of glass chewing, as I lovingly call it, but take a lot of effort to write down, and you have to be careful of keeping track of all of these random variables. Because of the notation we've specified, these proofs are going to be very simple. And you can think of them as kind of okay, now we have a bunch of Lego blocks. Can we combine them in a variety of different ways to construct, new tools from old tools with hopefully very little effort. So one of those tidbits is going to be in the homework, and we'll talk about it here. And so just to kind of get a feel for what it means to combine different tools using this notation, A and B, we're going to discuss another one of them, which is kind of a deeper one here in the lecture. And I'll give a proof of that, a very short proof of that as 3 or 4 slides that hopefully will be interesting. What we're not going to discuss here yet are things like the sparsity checks that appear in Fry. Those are going to be left for next lecture. Okay, so with that intro and caveat, let's get started. Unless anyone already has any questions, but feel free to. I'm actually staring this time at the questions point, so feel free to ping me at any point, and I can actually look at them. Okay, so as I mentioned before, last session was essentially pure math, right? So we didn't really say anything that was interesting unless you're already interested in math. So in this session, we're kind of going to start applying this math and saying things that are either familiar or, if not familiar, they would be useful in understanding zero knowledge protocols as we know them today. So the idea is, let's take the tools that we've kind of, we've done all this vegetable eating earlier on. Let's put those to the test. Let's actually, can we say interesting, real things about them that, in some sense, take what's known in the field and either generalize it or write it down in a simpler way. Okay, so as the high-level overview, one important thing that we use in the paper is this idea of models. And we're going to discuss what those things are, but essentially models will allow us to take what are pretty, hardcore cryptographic primitives and just kind of encapsulate them as a very simple way of modeling interaction between two parties. And in fact, we're actually not even going to model interaction between two parties. That's all going to be implicit in how we formulate the problem. So it's all going to be very kind of, magically, it's going to look very simple, but in reality, what's going on under the surface is actually fairly complicated. And that's kind of the cool part, as we saw with linear algebra. That's a cool thing that we can do is, we can encapsulate what are pretty complicated operations in a very small number of ASCII characters. We're going to do the same thing here, but with this notion of models. So in a sense, we're going to kind of, know in our heads that we're sitting on top of this cryptographic foundation, but never really discuss it because of the fact that we can think about that as kind of being abstracted away from our understanding. So from there, we're going to discuss specific tools. So specific tools are things like what I mentioned before, checking that polynomial is equal to 0 everywhere. And how does one do that in an efficient way? Well, it suffices to check that the polynomial evaluated at a random point actually equals 0. And so that's one such tool, and we're going to see an analog of that again via error correcting codes. But we're going to deal with, the paper deals with two types of checks. So those are what one call exact checks. This this thing is equal to 0 everywhere. The paper also talks about sparse checks, which are things like maybe this thing is not 0 everywhere, but it's 0 in a lot of places, and that is enough for us. So I'm going to leave those sparse checks. We're going to discuss it only a tiny little bit, but for the most part, they'll be left for the homework. And then if you are interested in the proofs of that, which are a bit more involved, for the paper as well. Okay. So the other way of putting this entire lecture is that we're essentially going to go build our toolbox of tools. Okay. So first, we've been discussing this notion of probabilistic implications. Right. And in this probabilistic implications, there's this notion that randomness plays a key role. So as we kind of do stuff, right, like there is this statement that depends on some randomness, right? And that allows us, hopefully, the point of this lecture was we will see that that allows us to simplify, take a big statement that's very difficult to verify and simplify it into a much smaller statement that's very simple to check, even though it has some probability of being false, right? So in particular, you might draw an incorrect conclusion from checking this one particular statement. But if that probability is very, very small, then that actually turns out to be fine for our intents purposes. So one very concrete example is going to be the following. We want to verify. So we are given some vector x. Right. So this is like, this vector x is sitting in some server somewhere, right? And we're allowed to access it. And we want to verify that that vector is sparse. In other words, that most of its entries are equal to 0. So we want to, for example, verify that less than 10% of the entries of x, at least 10% of the entries of x are non-zero. Sorry, at most 10% of the entries of x are non-zero. So in particular, 90% or more of the entries of x are equal to 0. Right? Why this is useful, discuss later, and it's again in the paper. But at a high level, it's like this problem, this like cool problem. Someone has handed us this. Someone's like, okay, I have this vector. You can like look at it by like looking at individual entries, but you'll pay a cost every time you look at any one entry, right? And essentially they say, okay, but I want to certify. I will tell you that actually most of this vector is 0, but I need you to certify that before you do anything. How does one do that? So if we kind of, like do this without thinking, right? All we do, I realized that for some reason, I guess the thing didn't finish compiling, but so essentially we can start checking, this big vector, right? We can start at entry 1 or whatever entry 1, and then just like simply check every element until we find that 90% of them are actually equal to 0, right? That's one method of doing it. That's huge, right? So if this vector is very, very large, and when I mean very, very large, say it has 1 million, 10 million, maybe 100 million entries, right? So if we're checking, that 90% of 100 million entries are equal to 0, that's kind of huge and insane. But we guarantee, that's one way of guaranteeing that like the vector actually turns out to be mostly sparse. On the other hand, of course, we have to do like 90 million queries for any of this to make sense, right? So it's a huge number of queries, and potentially like it's extremely expensive depending on how much we're being charged for every query that we make. Okay, so in the homework, we'll see that actually you can't avoid this. So in fact, this is unavoidable if you do not use randomness. So just keep that one in mind. Okay, but kind of getting back to that point, checking every single element, right? So yes, correct. This is the big O version of this. So checking every single element requires, roughly speaking, about n checks, right? If we want to check that 90% of the entries are 0, right, and we have n entries, then we need about 0.9 times n checks to be able to certify that at least 90% of it is 0. Ideally, it could be more. It could be, but the point is we want to certify this is the case. So the number to keep in mind is if n equals to the 20, which is about 1 million, then that's quite a bit of queries. That's about 900,000 of them. On the other hand, and you'll see this in the homework again, is that we care about, we don't care that like exactly, 10% of the entries are non-zero. We care that like at least 10% of the entries are non-zero, right? And so instead, with some notion of randomness, we can be certain with up to 2 to the negative 100% probability that this is the case with using less than 700 queries. And so the high level idea is what you're going to take, you have this big vector, and you're just simply going to randomly sample entries of that vector, right? And you're just going to check if that entry is 0. So you start with a big vector. You say, okay, I'm going to choose a number between 1 and 2 to the 20. Let's say it's whatever, 132. I'm going to check if entry 132 is equal to 0. If it is, great. If it's not, then we fail immediately. And so the idea is if all of those entries are, if all of these randomly sampled queries are 0, in other words, 700 of them are 0, then we know that the vector must be pretty sparse with very, very high probability. So again, I'm not going to discuss the exact probability theory there. It's kind of fun. It's not super hard. It's kind of fun. And the point is that it's going to be in the homework. Okay. So with that, right, we can kind of see like where randomness helps, right? Like randomness is very nice because we start with a problem that if we did it deterministically would require us to have a huge number of queries, a very large amount of interaction between two parties or between, us and some data that's out there or whatever. And randomness kind of allows us to reduce that by doing this kind of small, let's call it a Faustian bargain, which is now you're not allowed to know that this is true with 100% certainty, but you can know it with enough certainty that for all intents and purposes, it might as well be true. Feel free to close your ears if this is already satisfying for you. There's a whole question around what it means to be random, and that's pretty complicated. And I'm pretty sure there are entire books written about this notion. So we are going to assume a kind of a very idealistic version of randomness, which is pretty close in practice as far as we can tell. Again, thanks to cryptographic techniques. But the point is, the randomness here that we're going to consider is going to be the simplest possible thing, where we say, okay, things are drawn uniformly from some distribution, and that's 100% fine, and we can achieve that, by whatever means necessary. Okay. So let's talk quickly about models. So as I mentioned before, models are how we can encapsulate kind of deep cryptographic techniques and interactions that happen between parties as a very simple kind of high-level interface, if you're familiar with programming. So in particular, models are going to be, as I mentioned, right, the way that we encapsulate all of this kind of complicated stuff that happens in zero-knowledge proofs, interactions and cryptography specifically, in a way that we can access relatively easily with no problem, kind of dealing with a high-level math constructs. So the point is we can kind of separate these two things out, right, in such a way that like we assume cryptography works, and we assume the kind of like interactions work in the way that we expect, and we can, if we assume that, right, and we now have this very nice interface that we can play with that lets us write very clean proofs about how the rest actually works. So for this lecture and in general for the paper, we have two models of interaction. Okay, the first model of interaction is what we're going to call the direct model of interaction, or the direct access model of interaction. So in this model, this is very similar to the problem that we just recently described regarding kind of checking the sparsity of a vector. So in this model, there exists some vector x, and the vector x is kind of out there somewhere. I'll give you a concrete mental image of what this means later. And the point is, we would like to verify some claim that someone made about x. So the claim, for example, before could have been that x is actually has a sparsity of 10%. So 90% of the entries are 0. At least 90% of the entries are 0. And in this model, the only thing we're allowed to do is query individual entries of x. And every time we do that, we pay some cost. The cost is left unspecified, but the point is we care about the number of queries that we do in order to verify this claim. Okay. So the way to think about this model is you have a, like a little hard drive, right? So, and someone tells you, I need you to verify this thing about X, and they hand you a hard drive, and the hard drive is truthful. So in particular, you can plug that hard drive into your computer and then just like verify the things that you need to verify directly. But the point is that because the hard drive is this passive thing that exists, right? The person who is like telling you like you should verify this claim cannot adaptively respond to your questions, right? In some sense, this is like this model of like, okay, I have a thing that's out there and the responses happen. So when I query X, I'm actually querying X. I'm not like querying some party out there that is like attempting to fool me in some smart way. I am simply actively querying X. You might think that is, that's kind of weird, right? Because it's very rare that we can do this. And we're going to discuss how one does this, in a second. But the point is, if you assume that you are querying X, right, in some sense, you've encapsulated some notion of like interactivity between you and kind of the thing that you're looking for. Okay, so that's one model, right? This direct access model where you directly get to look at the entries of X. The second model is called the coding model. In the coding model, there is a public code matrix or a public error correcting code matrix, G. Right. G, as usual, and as will be standard for pretty much the remainder of the sets of lectures and throughout the paper, is an M times N matrix. Okay. This code matrix is known. So it is known to everybody. It is certainly known to us. And much like the previous case, there is some message that we do not know ourselves, like lying somewhere out there in space. And we would like to verify a claim about that message, so that message X. In this model, we're not able to access X directly. So we're not able to look at, entry 3 of X. But we are able to query a symbol of the encoding of X, right? So if you remember from the previous lecture, when you have an error correcting code matrix G, you can take a message, X, so in this case, X being the vector that we're checking stuff over is our message, and then simply multiply G times X, and that's called the encoding of X under the code G. Okay? And from, what this model says is, okay, you're not able to access X, but you are able to access one symbol, so one entry of the encoding of X. So I cannot access X3, but I can access, the third symbol in the encoding of G times X. In other words, the third entry of G times X, right? So G times X is a vector. I simply look at its third entry. And the point is, I now pay a cost proportional to the number of symbols I have requested. Okay, so that's called the coding model, and this is the one that we're actually going to focus on for most of this lecture. And again, I'll get to how one achieves this in practice, but the idea is relatively similar. It's someone hands you a hard drive, right? And the hard drive has a little chip on it that simply encodes, the message X, and then spits out it doesn't spit out the whole code word, but it spits out a specific entry of the code word corresponding to the message. So it spits out a specific symbol of GX, the one that you requested. And again, it is assumed to be truthful. So, okay. So, I alluded to this fact that like, this is a very strong claim, right? Like I'm telling you like, oh, there's a message X and you have access to it. It's a very strong thing to just be able to do, especially in things like zero knowledge where you might not actually trust the other party. So the models by definition require this notion of truthfulness. And the point is that this truthfulness actually, thankfully, people much smarter than me have been working on this idea for like a very long time. And they're like, cool, like here is a black box that allows you to guarantee a certain notion of truthfulness. And that notion of truthfulness is achieved via cryptographic techniques. So one example of it is in the direct model, right? This truthfulness notion, this fact that you can actually query individual entries of X, can be achieved by just a Merkle tree construction. How does that work? So again, if you don't really care too much about this, like close your ears for a second. This is, but it is a very important point, and it is like very interesting. Is instead of a person giving you a hard drive that says, here is X, please check this thing that I need you to check. They hand you the Merkle root, right? And then you can query them. You say, okay, I need you to give me entry, as we discussed, 132 of X. And they give you the entry, and they give you a proof that that entry actually was somewhere in one of the leaf that 132 of this particular Merkle tree. And it says, cool, okay, here you go. Here's X, and here's a proof that the thing I sent you originally is consistent with the answer I just gave. And in some ways, that's like a way of encapsulating this fact that you were able to access the original X that people wanted to verify, without any kind of without the party trying to mess with you, without the party trying to be like, oh, I know what, Guillermo's going to ask for in the next step. So I'm going to try to fool him by sending him just the right information to make him be like, okay, this check passes. Okay. So if you close your ears, feel free to open them now. The point is all of this kind of, this deep cryptographic techniques are going to be completely elided. They're going to be black boxed as its own separate kind of ideal. We assume that this thing works. We assume that we can access elements of X directly. We assume that we can access code words of X, specifically symbols of a code word. How that's achieved is usually via the notion of commitments. But that's, that now that has been black box, we can move it to the side and then focus on now purely the linear algebra part of ZK proofs. Okay. And of course, I will note that this is, of course, a super fascinating subject and of course worth studying. And this is a bunch of cryptography that's super interesting. Okay. So let's now talk about the exact checks. So here's a question. Randomness plus hashing used in a construction gives the same concept as a digital signature. Is the concept similar? So signatures, I think you can use some sort of signature schemes to construct commitments, but in general, they're not equivalent. There's a notion of a commitment that is very specific. At a high level, a commitment simply says something like, I am going to give you kind of some number, something X, right? And then that essentially forces me to ahead of time commit to a fixed object that I cannot go back on. So because I gave you this, yes. So the question was, I'm going to read it out loud. I'm going to try to map it to something that I think is direct, which is randomness plus hashing used in a construction gives the same concept as digital signatures. Is that concept similar to what I explained previously? So at a high level, just this notion of signatures and commitments, they're somewhat, I think, related. And again, I'm pretty sure there's some notion by which they play together, but a commitment fundamentally is a different object. A commitment is a thing that lets me send you some, object, whatever that is, right? So in particular, it's a commitment, but and then you can query me. So you can say okay, please give me, something about this object that you have committed to. And the point of that commitment is in some ways, I cannot go back on my word. I cannot go back and answer you in the way that I want if I wanted to fool you in some way, right? So I can only answer you truthfully based on what I've committed to. So if you think about it, there's some magical object X in the sky, right? I have a commitment, which is a thing that depends on this object. I give that to you. And then you ask me, oh, cool, is X a dog or whatever, right? I can't go back and be like, oh, actually, yeah, totally, 100%, even though X is whatever, something else. So that's kind of a weird version of it, but at a high level, the point is, yes. So specifically, we're going to look at the binding property here. So hiding is not going to be super important, but and this was mentioned in the chat, I guess, but the point is we're going to be looking at this notion of a commitment, which is very useful, but it's going to be encapsulated magically within this kind of model, this access model. And so we won't talk about it anymore other than that. Okay, so let's go through to the exact checks. Again, hopefully you close your ears for another second between that question, what I'm about to say. So the exact checks now we're going to now start discussing things that generalizations of things that kind of exist out in the literature in various implementation. So from before, exact checks work in this notion of a coding model. So in the coding model, if you remember, we start with some message and we're allowed to access, symbols from the encoded message, right? It turns out like exact checks, so checking, for example, that a vector is exactly equal to 0 is actually very hard in the direct access model. And we'll prove that in order to succeed with high probability, you actually essentially need to check every entry of x for something to be. If you want to check that x equals 0 and you only have access to the direct access model, essentially you're going to need to check pretty much every entry of x to be guaranteed this thing. Okay. Please see the homework exercises, Okay, so here's the setup. And this is going to be fixed for the remainder of the presentation. So feel free, I would recommend if you have a cheat sheet next to you, this is the thing to write down. For the remainder of this section, we're going to fix a code matrix, G. And G, as before, is going to be an M times N matrix, drawn from whose elements are in the field F, but doesn't matter. The next thing we're going to fix, so the code always has distance D. And ideally, we're going to assume that D is going to be greater than 0. Otherwise, everything we say is going to be trivial. The symbol R will just be a uniformly drawn number from 1 to M, right? So YM is because we can think of R as choosing a specific row of the code matrix G. Similarly, one way of thinking about it is if G, if we encode a message X via G, so we get G times X, then what we're going to be doing is we're going to be drawing the rth symbol of that encoding, right? So R is a uniformly drawn number. G times X is an encoded message. We're going to be drawing the rth index of that encoding. Okay. So let's start with the simplest check. This is classic. So this is, I want to check that something is equal to 0 or not equal to 0. A vector, ideally, is equal to 0 or not equal to 0. Certainly, I can do that for a number. If it was a number, that would be super easy. I simply just check that number. But if I have a vector with, a million entries, checking that whole thing is 0 is actually pretty non-trivial. Okay. So how do we do that? Here is one simple idea. I'm just going to sample R. So I pick an R between 1 to M, and then I'm just going to check, is that symbol that I've just sampled equal to 0? Okay. So everybody get this. So we are handed this hard drive, spits out, I get to request indices, and then it gives me a symbol from the encoding. So it gives me an entry of G times X. And all I'm going to do is I'm going to sample a random number, and then I'm going to check. I'm going to be like, please, again, I sample random number 132, our favorite random number of this lecture, apparently. And I'm going to check, I'm going to say, please give me entry 132 of this vector, of this, encoded message. It's going to say, okay, great. Here is your number. And then I'm going to check if that number is equal to 0. That's the only thing that happens here. And it turns out this is actually a very effective check. So specific, we can write it in probabilistic notation, which is going to be useful very soon. As, okay, G times X, so that's, again, an encoded message. I check this rth symbol. I check if that's equal to 0, right? That's a statement that I'm making. I'm saying I have checked this thing, the rth symbol, where R is some uniformly randomly drawn number, and that's equal to 0. And that, if I check that statement and that statement is true, then with probability, with error at most P, that's going to imply that X actually equals 0, right? And P here is defined as the following. It is 1 minus the distance of the code divided by the number of rows of G. In other words, divided by M. Okay. So parse this pretty carefully. I'm going to leave this up for like 10 seconds. But what are we saying? Again, we are taking a claim. So the left-hand side, parse it all very carefully, is a scalar quantity. So G times X is a vector. We take a random entry of that vector given by R. That entry is, of course, a scalar, right? So that's a number. And we simply check if that number equals 0. And it seems super obvious, but it's kind of crazy. That, just doing that, is enough to guarantee that the entire vector is 0 with high probability, right? We have reduced checking a potentially very large vector to checking that a single number is equal to 0. right? Whereas, sorry, we're just checking that an entire potentially very long vector is equal to 0 to simply checking that a single scalar is equal to 0, right? Using the notion of randomness. Not multiple rounds, just doing it once. Multiple rounds will give us a better probability estimate, but it turns out for almost all intents and purposes, this is very, very good. So, and before, as given before, the probability that this check fails is at most 1 minus the distance divided by the number of symbols in the encoding. Okay. So I'm gonna give you some intuition for that bound. It's pretty simple. Pardon my crappy drawing. If someone wants to, do a pull request and tech this up, that would be great. So that's another extra credit homework assignment. But we start on the left-hand side with some vector. X is not equal to 0. And let's say that the vector is created in such a way to like maximally trick us, right? So it's done in such a way that like, it has like one entry that's non-zero, okay? By definition of the distance, right, when we encode that vector, because that vector is not equal to 0, the distance of that vector, in other words, the number of non-zero elements that are in the encoded message is at least d, right? So if x is not equal to 0, then there are at least d elements in the encoded message that are also non-zero. That's the definition of distance. That just comes from, the thing that we wrote back in the good old days of the first lecture. I guess that was 2 days ago. Okay. So because of that, if we randomly sample an entry of g times x, right? So we randomly sample an entry of the encoding. There are m entries in the encoding. That's the definition of our encoding. At least d of them are non-zero. So that means that the probability that we catch, the liar is d divided by m, which is the same thing as saying and that's an at least, right? So it could be more. There could be more entries that are non-zero, in which case it's better for us, but it is at least d over m. Okay. What happens? What is the probability then that we fail? Well, it is at most the probability that we, catch one entry. Well, at most 1 minus the probability that we like pick out a non-zero entry, right? And so you get something like 1 minus d, which is the number of non-zero entries, divided by m, which is the number of all possible entries. And that's the probability that our check fails. So it's the probability that we like look at an element and it happens to be 0, but the vector itself actually turns out to not be 0 in the first place. Okay. So cool. There are 2 questions. I'm not fully sure I understand them, so that's okay. I'm going to skip it for now. But the high level idea is you only need to do this check. This is a bound for only doing the check once. In many cases, d divided by m is going to be a very, very, very small quantity. So it could be something like 2 to the negative 200 or 2 to the negative 220. And so that's essentially like impossible. In some cases, it's going to be better, but not, Okay. So at a high level, actually, and maybe I'll make this a homework exercise, is actually this exact statement is equivalent to the one-dimensional Schwarz-Zipf lemma. So this is the error. This is the general linear error correcting code generalization of the Schwarz-Zipf lemma or the polynomial zero check or something of the like. And indeed, we find that Schwarz-Zipf is actually exactly the special case where the code that we are using, the code matrix G that we are using, is a Reed-Solomon code, where we essentially like every single row or every single possible element is included in the matrix. That's in the paper. I'm not going to discuss it too deeply here. I might make it a homework problem, but at a high level, the point is that this is a strict generalization of kind of Schwarz-Zipf to general linear error correcting codes. Okay, so now let's kind of do something a little bit weirder. Let's say we don't want to check a vector is 0. There is a question here, but I'm also going to defer this one because I'm also not 100% sure what it is asking. So yeah, if you If you want to rewrite the question or maybe ask in a slightly different way, I might try to map it to something but I just not quite sure what the question is. Okay, so let's pop over the matrix 0 check. So let's say instead of a vector x, we actually have a matrix. And this is a big matrix. So it's a matrix, as we know, is a collection of vectors, each of which is a column. And there are n vectors in this matrix, each of which is k long, right? So there's x, capital X is f, to the k by n. And so we're going to ask the same question. Does the whole matrix equal 0? Okay. So one big idea is, okay, cool. We can encode every row. So instead of, let's use our previous magical deducting tools. It's like, okay, we know how to check if a vector is 0, right? Can we do that for a matrix? Well, yes, right? Let's, take a random element from every row of X, from the encoding of every row of X, and then check if that is 0, right? So this is, written in our notation is we're going to let x tilde I denote the ith row. So we have a matrix X, right? It has a bunch of rows. I want to just take those as vectors. And then we're going to say, okay, please encode that for me, and then give me the rth symbol of that thing. So give me the r symbol of the encoded first row, the r symbol of the encoded second row. And know that this r is the same. This is not a randomly drawn r for each one of these. This r is identically the same. And then let's just check if each one of those things are 0. So all of, we have n things that we need to check are 0. We simply check this magical thing, and we're, the point is that this gives us that if you check all of those things and each of those things is 0, then with probability p, the capital X must have also been 0. The whole matrix must have been 0. So if we encoded every row, we check the same random index from every single row that we've encoded, and we check out all of those are 0, then indeed the whole matrix X must have been 0 with high probability. Okay. And so I asked you this question, which is what should P be here? And as the easiest hint is, I would recommend you see homework 1, exercise 5. So if you did homework 1, exercise 5, the thing on the left-hand side should look very familiar. And you have to parse what that means for the thing on the right-hand side. So if you did that, you should be able to reconstruct what P is here based on the 0 check that we just discussed. Okay, so here's another way of rewriting this is, okay, instead of writing it as let's encode each row and then check if a random symbol from each row is equal to 0, let's do it the following way. This is the same thing as saying, let's pick a random row from the big matrix G, right? So G is our code matrix. Let's pick a random row from it. And we're going to use the row as the weights for a linear combination of the columns of X. So if we recall, X is a collection of vectors, each of which is a column, right? We want to take a linear combination of those columns, right? And what are we going to use? Well, we're going to use the randomly drawn row from G, right? So those are going to be the weights for the linear combination. And what are we going to do is we're just going to check that the entire linear combination is equal to 0. So that is a vector, right? We've taken the linear combination of vectors, gives us another vector. And we're going to check if this vector itself is equal to 0. Another way of writing exactly the same check that we just did in the previous slide is the following, which is exactly what I just said. It is we take the rth row of G, and then we simply use those as the weights for a linear combination of the individual x's. And because it's just the same thing that we said before, just written slightly differently, that is going to imply that the whole x equals 0 with the same probability as previously. Okay. So does this make sense? Is everyone good with this? Okay. So let's get funky. Here's a fun fact, right? The vector 0, what is it doing? Like at a high level, we essentially like the vector 0 check takes a vector, right, which is our message, and then somehow reduces checking that vector equals 0 to checking that a single scalar equals 0. There's some randomness and some stuff involved, but whatever. At the high level, all we have is we start with a vector, right? I want to check out the whole thing is 0, and then we reduce that problem to checking that a single scalar equals 0. Okay. The matrix 0 check starts with a matrix. It asks the question, does a matrix, do all of the entries of a matrix equal 0? And reduces that question to whether all of the elements of a single vector equal 0, right? So the natural question is, can you put those two things together, right? We've reduced a matrix to a vector, right? We've reduced checking that a matrix equals 0 to checking that a vector equals 0. But we know how to check whether a vector equals 0 by checking whether a scalar equals 0. So can you put those two things together and get kind of, some sort of bound on the probability of error? And the answer is yes. And that is going to be an exercise for the reader. And that is one way of getting kind of, used to this notion that you can chain probabilities together, that we discussed a little bit in the previous lecture, but we never actually used until now. So, okay. So for the nerds in the room, like me, this idea that you can kind of take a matrix, reduce it to a vector, and then reduce that to a single scalar, is actually a generalization of Schwarzschild. If you just naively apply the kind of probabilistic implications, as you'll see in the homework, you're actually going to get exactly the same Schwarzschild lemma if the matrix G is a Reed-Solomon code matrix. But it turns out it's actually not tight. So we discussed this in the ZK Hack Discord, which is this notion that the probabilities add together, but like just because the probabilities add together, that doesn't mean that the resulting probability is tight, right? Like these errors can kind of add, right, using our notation, but you might be able to actually do better than that, right? Because by using more structure from the problem or something of the like. And the point is, this is one of those cases where you can actually do better than the naive approach of simply kind of chaining these implications together by using more structure available in the problem. And so I certainly won't discuss this, and I don't think I'll put it in the homework, but it's in section 3.1.3 of the paper. And it actually shows that Schwarzschild is not tight even for polynomials by a very, very small factor, which is roughly the square of 1 over the size of the field or something like that. Okay, so that's, slash nerd. So that's the nerd rant is over. Let's continue with the final boss, which we're going to call the vector subspace check. And here is we're going to put a bunch of stuff together, and it's going to be a little bit magical, but it's going to be very succinct and very short. Okay, so let's start with some matrix X. Again, same dimensions as the previous matrix, so K by N. And instead of checking if all columns are 0, we're going to check if all the columns belong to a subspace V. And if you remember from homework 1, there is a special case. So the 0 subspace, in other words, the subspace that only has one element, which is the vector 0, is a valid subspace and exactly reconstructs the matrix 0 check that we had before. So anyway, so that's a special case of this. This is a more general claim. So again, we want to take a bunch of columns of X, and we want to check whether all of them belong to a vector subspace V that we know. And there's a question of, can we do this cheaply? So can we do this in a way that doesn't require us to verify every single column of the matrix X? Okay. So let's do something very similar to what we did with the matrix 0 check, the rewriting of the matrix 0 check. We're going to pick a random row R of the error correcting code matrix G, right? And then we're going to use that random row as the weights of a linear combination of the columns of X, which is the matrix that we wanted to check to see if the columns of X belonged into this vector space V. And then we're going to check if not the individual columns, but if the linear combination using that randomly sampled row also lies in the space V. Okay, so all we did was we used the same trick that we used before, which is we're going to randomly sample a row. We're going to use that as kind of the weights for a linear combination of the columns of X. And then we're just going to check, instead of that being equal to 0, like we did before, we're going to check if that thing is in a vector space V. So if that whole sum, which is a single vector, lies in the vector space V. Okay. We can write this in the probabilistic notation as this simple thing, which is G of R1. So this is the rth row of G, the first column, times X1, which is the first column of X, plus the linear combination of every single column in capital X. If that is in V, right, in the big vector space V, then that implies with high probability, or in other words, with error at most P, that every individual entry of X, or every individual, column of X, in other words, each Xi, must have also been in the vector space in the first place. Okay, so let's do a quick proof of it. So this is where the linear algebra comes in. So we need C, which is going to be a parity check matrix for V. If you don't recall what that is, you should take a look at the homework and or the paper. So then what happens? Okay, we have assumed that our check succeeds. So in other words, that G of R1 times X1, the linear combination of the columns of X, are indeed in V with this randomly drawn row R. So if that's in V, then by definition of a parity check matrix, C times that whole vector must be equal to 0, right? Because by definition, a vector is in V if and only if C times that vector is equal to 0. Okay. Now, by linearity, if you remember, C is a linear operator. So we know we're going to take the right-hand side here of the first implication. All we did was move it down here to the bottom left. But C is a linear operator, right? So C is a matrix. And so C times the sum of a bunch of vectors is the same thing as the sum of C times every single vector, right? So another way of rewriting that is saying, okay, C times, the linear combination of the xi is the same thing as the linear combination of C times the xi's, right? Which is the equality that we have here on the right-hand side. So the right-hand side, we have, a randomly drawn row of the matrix, of the code matrix G, right? And we're using that as a way to linearly combine C times x1, C times x2, all the way to C times xn. And we know by definition that that whole thing equals 0 for the randomly drawn thing. Yes, so someone's getting ahead of me, but yes, exactly. So all I did, this is just simply taking the last equality that we had in the previous slide. I put it back up here. But this should be familiar, right? This last equality that we have right here. So again, I just took the right-hand side of the bottom. So I took the bottom right-hand side and just moved it up there. I didn't done anything to it. If you recall from, 10 slides ago, this is exactly the matrix 0 check, right? What was the matrix 0 check? The matrix 0 check said, take a bunch of vectors, take a random linear combination of them using the randomly chosen row of G, and check if that whole thing is equal to 0. If that is true, then we know that each of the individual vectors must have themselves been 0 with high probability, with error at most p. Okay. But by definition of a parity check matrix, if C times X equals 0, then X must be in the vector space in the first place, right? So this gives us, if we kind of put all of the implications together using the rules that we know and love that we've been talking about, this gives us exactly the claim we wanted, right? We put everything together. We start with take a random linear combination using this like random row of the columns of X and check if that is in V. And that, if you follow all the implications, implies at the end of the day that the columns themselves must have been in V in the first place. Okay, so we only used one implication with any error, and that was the matrix 0 check. The rest were all just normal standard logic implications. So they have 0 error, and so they add 0 error to our conclusion. And so in other words, if we put everything together, we can write exactly the claim that we wanted before, which is it suffices in order to check that all of the xi's lie in so all of the columns of X lie in a vector space V. It suffices to check that a randomly drawn, a random linear combination of these, where the linear combination weights are given by a random row of G, also like that linear combination lies in V, and that has the same error probability as the matrix 0 check that we had before. Okay, so anyway, so this is kind of crazy, right? Like we just did a proof in like 2 slides of like something that I think is pretty non-trivial, and would be pretty hard to do if you just like looked at it from scratch and were like, okay, yeah, let's do this. So I would recommend going back through the slides and parsing it a little bit more carefully. I went through it a bit quickly, but all of the symbols have a specific meaning and everything makes sense. And you should look at which quantities are vectors and which quantities are kind of matrices and things like that. It's worth doing just carefully. Okay, so quickly through sparse checks there is to every kind of check that we just recently talked about, there is a sparse version of it. So there's a version of it where we actually don't care that the condition is exactly met. So for example, maybe X is not exactly equal to 0, but it's sparse. Or maybe X is not exactly in a vector space, but it's close to a vector space in terms of distance. We're not going to explore the proofs in this particular course because they're quite complicated and some of them require actually a bit of annoying glass chewing. But I would recommend you check the paper and the homework, which is related to first set of exercises I was talking about for some of the proofs there. Okay, so essentially for the next lecture, which is going to be kind of the icing on the cake, we're going to use two types of sparse checks. So one of them is going to be in the homework, which is going to be the standard sparsity check, which was, again, the same thing that we discussed in the very first set of slides, like at the very beginning of this lecture. And then the other one, I'm going to give you an outline of the proof in the next lecture. Unfortunately, for this paper, I found no easier way of proving this thing. It's not clear to me that there is, because it kind of relies on a bit of, deep, it's not that deep, but like somewhat deep linear algebra. But if anyone, that's a great exercise. If anyone wants to go ahead and try and find a nice proof of it, that would be super useful. But I'll give a proof outline of why, this certain sparse check is true in the next lecture, but we won't cover the proof of it. So apologies for that. You'll have to go check the paper. But the main thing to note is that it's really good to be comfortable with this kind of probabilistic notation before that lecture. So I would highly recommend you do potentially things like problem 5 of this previous set and maybe the first or second of the problems of this next set. Okay. So where to from here? Okay, so fine. We rewrote a bunch of tools, right? And we rewrote Schwartz-Sybil and a bunch of like other similar things. Some of them hopefully felt familiar if you know a bit about kind of ZK and stuff like that. But the point is that we did all of them, and we covered all of these things in a span of 30, 40 minutes or something like that. So this kind of shows you the power of the notation and the ability to kind of take a bunch of things and imply one versus the other, and concatenate them in a variety of ways, and kind of really think of them as mathematical Legos that you can use to place things together, right? So that's kind of the high level idea here. Now you have a bunch of tools in your belt, and it's when you look at something, it's kind of easier, hopefully, to see how the pieces fit together, as opposed to kind of being this kind of monolithic single, big proof that you have to think about entirely before you understand it. So in the next lecture, we're going to see how we apply these tools to explain this security of Frye. It's a very weak notion of security yet again, and constants aren't good. And then people ask us all the time, they're like, "Oh, do you get better constants?" And it's like, we know we don't. This is not trying to improve the analysis of Frye. It's simply trying to understand it in a simpler way and show certain notions of security. It's very possible that you can do better. In fact, I know you can do better in terms of constants than our paper, because simply we made it the simplest possible exposition rather than like the fanciest possible kind of most refined set of constants. But the point is, this will serve as a kind of capstone project, right? Like, so far everything has been, the first lecture was very abstract, just pure linear algebra. The second lecture, this one, is a little bit less abstract. You've probably seen some of the tools here if you're familiar with ZK, but the applications of them are kind of probably not quite gelled yet. And here we're actually going to see just a very concrete application of a number of the tools that we explored here, directly into proving kind of something that we know and love, and actually turns out to be like very hard to understand. To me, it was, at least, which is the kind of why does Frye work, right? Like, sure, it's possible to know how these checks work, like that, and possibly intuitively it's clear that they should work, but like, why does it actually work, kind of fundamentally? But the point is, that's just going to be kind of a cool application. That's the best way to think about it. The idea is with this is that there are hopefully many more applications of these tools to explaining a number of other ZK systems that might be useful and interesting in a variety of different ways. So I encourage you, as you kind of go through these things, a fun exercise would be to rewrite some of the proofs that people have in certain other papers using this notation, potentially maybe generalizations to linear algebra and things like that. So cool. Thank you all for coming. I have about 4 minutes for questions until 10 a.m. I can stick around until afterwards. This one ran a tiny little bit longer than I expected, but feel free to ask any of them and things like that. Great. Thank you all.
Thank you very much. So yeah, if anyone has questions, you can either ask them in the chat or request the audio and video to ask them here. And if you don't and you're already working on the homework, that's fine too. I guess you're gonna be posting them on the Discord as last time.
Yes. So a quick note on that, I guess, since there's no major pressing questions. There's two things. So I'll probably be posting the homework hopefully by Monday for next one. Look, if anyone's already finished all the homework already, big hats off to you.
That's good. You leave us time to finish the first one. I did not, for instance. So thank you for not putting pressure on me.
What is this? The model student isn't finishing, the homework like 3 days before class.
I'm really not a model student. You should ask my mom. But yeah.
So that's part one. So sorry about that. I need to edit them a little bit more, and then there's some stuff that I want to make sure I add problems for. And then number 2 is, and this is kind of a big one for anyone who's interested in solutions. I don't have solutions. I mean, I know the solutions and I need to write them down, but anyone who's interested in writing solutions should go take a look at the repository. I posted it in the ZK-Hack Discord, and you should feel free to do a pull request. So if you have a solution and you can write it up in LaTeX, please do a pull request. It would be great, by the way, if you did people did pull requests either per part or per problem, because I don't want it to try to merge a 500-line pull request. Is actually kind of annoying. So I will also give you a fair warning that I'm a pain in the ass about writing. So we'll take a lot of editing probably before it goes on to the thing. But know that it is with love in my heart to make sure it's all clean. By the way, if there's errors in slides and things like that, also feel free to pull request those or raise an issue in the GitHub, and I'm happy to edit it or accept the pull request or edit it as needed. Things like that. Okay, cool. So there's one quick question, which is does the sublinearity of verification, aka succinctness, stem from the probability of queries according to M for this instance? So I think so the way I interpret this question is, okay, does the fact that verification, is cheaper than kind of like checking the original claim, does it stem from kind of this notion of randomness? Okay, cool. So the answer is yes, actually. So you cannot have, and you'll see this in the homework for a very specific claim, you cannot have succinctness, you cannot have sublinearity of the verification without this notion of randomness. Like, it is actually impossible. And you're gonna prove an impossibility result in the homework that says, like, you cannot actually check that a vector is like all equal to 0, by just like checking its entries, unless you literally check a linear number of entries in like n, in the size of the vector. So that'll be an interesting homework problem that will hopefully elucidate that question a little bit more. Anybody have any more questions? Can we apply this kind of logical operation to any other math logical operation? Yeah, so there is, the paper actually does have an if and only if version of it. So there is a notion of if and only if. In fact, there's a notion of a lot of the logical implication rules, not just implication rules, but logical rules, in this kind of weird setting. So the exist symbol is a bit funky, and there probably is something like that. So because existence is not a logical notion, it is a set theoretic notion. So it's a bit different. The equivalence is indeed the case. So logical equivalence works in the same way. The if and only if also works, but actually it turns out you actually don't always want if and only if, because it turns out one direction is always true. So for example, if you have a bunch of things that are 0 and you multiply them by anything, you add them together, it's still going to be 0, always going to be 0. So there's no probability of error in one direction. That's often called completeness in zero knowledge proofs, right? But in the other direction, the soundness error, right? There's a probability that indeed the notion is false. So this actually, what's interesting about the notation is that it very cleanly separates out completeness, right? Like, there's no notion of completeness that we talked about here. We kind of use it implicitly throughout, in the sense that, like, we expect the check to work if the claim is true, but we don't actually ever like mention the fact that the check, if, for example, if x as a vector is equal to 0, then certainly g times x is going to be equal to 0, right? So the check is always going to pass, but we never talk about that in this lecture, right? So in a certain notion, like this idea is like completely separated from these like probabilistic implications that we talk about, right? Those implicitly assume that the check that you have done is satisfied, and then show that the original thing must have been satisfied. But it is possible the check that you do might be too restrictive, right? Maybe it actually almost never holds or something like that. The only thing this claims is that if that check holds, then the conclusion probably holds with very high probability. But it need not guarantee that even if the conclusion holds, that the check does hold itself. So, but the point is there are equivalent versions of these, implications and things like that, and you can construct versions of it where you have like asymmetric implications, or one way is 0 and the other way is probability p and all this stuff. Okay. Cool. Any further questions?
it looks like it's a wrap for today. So yeah, thank you everybody. Thank you, Guillermo. And yeah, we'll see you next week. Make sure you register to the event for next week. It's going to be a new one. And yeah, in the meantime, have fun. Good luck with the homeworks. And yeah, let's study the part 4. Next time is going to be the part 4, right, of the paper.
Next time is the part 4. It's a little bit of end of part 3 and
end of part 3.
part 4.
Yeah, exactly.
So yeah, thank you, Gaylord, and thank you, Anna, for having me, by the way.
Yeah, thanks everybody, and see you
All right.
soon. Bye-bye.
Ciao, ciao.